Hello everybody, hope you're doing well. This is paper 2 from November 2023 and this is time zone 1. Now let's have a look at it and see what we can do. Next question, 18 mark question. The running time T minutes of 200 family movies are recorded in the following table. So you have this group frequency table here. And we want to write down the mid-interval value of T is greater than 70 and less than 80. So first off, what's going on here in our group frequency table? Group frequency table breaks up a total sample into class intervals. So what they're saying here from this T is greater than 70, less than 80, is we have 11 movies and their runtime, or the length of the movies. We have 11 movies between 70 and 80 minutes. And 51 movies between 80 and 85 minutes, and 68 between 85 and 90, and so on. First question, they're just asking, write down the mid-interval value of 70 and 80. So when T is greater than 70, greater than or equal to 70 and less than 80. The mid-interval value is essentially the midpoint, the halfway point. And the mid-interval value of 70 and 80 is 75. So we can just find the average between the two. Calculate an estimate of the mean running time of the 200 movies. So let's see what we can do there. For this question, remember the IB often will present one question that will then kind of scaffold or give you a cue of what's coming next. So the first question, we had to find the mid-interval value, and we'll actually make use of that. That should be a kind of cue in terms of how to approach the rest of this question. So we have 200 movies, and we want to find the mean running time, or the average running time or length of these movies. And we don't know the length of the individual movies because they're already grouped together. So just looking at this first one here, where we have 11 movies between 70 and 80, and the mid-interval value of 75, we can look and we can ask ourselves the question, what is the average length of these movies? And it's possible that the movies are, let's say, 78 and 79 and 77, and they're all clustered towards the higher end. But what we're imagining is that these movies are roughly evenly distributed. That is to say, there's a 71, a 73, maybe a 75 and a 79, but on average, if we were to take these 11 movies, the average runtime would be roughly 75 minutes. And same thing for this 51 minutes right here. Right here. We don't know the lengths of the individual movies, but on average they're 82.5, and same here for these 68 movies. This is 87.5, 92.5, and this last one, the average would be 100. Okay, so these are all the mid-interval values of these movies, or the average runtime, and that's going to help us if we want to find the overall average of these 200 movies. So what is our average? How can we find the average? To be honest, there's actually an easier way using spreadsheets, but calculate an estimate of the mean running time of the 200 movies. A 3-mark question sounds like they're going to want to see some process. So the average, which we can also call X bar, is equal to the sum of all values. So we're taking up every single runtime of all of these movies, adding the length of each of these movies, sum of all values, divided by the, in this case, the number of values. So in this case, the number of movies. So the number of values. Maybe this is a little hand-wavy of an explanation. The sum of all the values. We add up the lengths of all the movies, and then we divide by the total number of movies, and that'll give us the average. So, if we want to find the average, we can use these mid-interval values. So there's 11 movies, and the average runtime was 75. And for here, we had 51 movies, and the average runtime of these movies was 82.5. We had 68 movies, and their average runtime was around 87.5. And so on for these 47 movies. And lastly, for these 23 movies, on average they were about 100 minutes. And altogether we had 200 movies. And so let's find the average running time of these 200 movies. So let's go back to the calculator for a sec. So 11 times 75 plus, I'm going to work out the numerator and then the denominator. 82.5 plus 68 times 87.5 plus 47 times 92.5 plus 23 times 100. And this will be the lengths of all the movies added up. And we had 200 movies, so we'll take this and we'll divide it by 200. So this is every single movie, and we've added up the total length of all the movies combined, and we don't divide it by the total number of movies. This tells us that the average length of these movies is 88.15. So let's go ahead and write that in. 88.15, or to 3 sig figs, 88.2. Okay, this is a 3-mark question, and I believe that's the way that they're kind of nudging or suggesting that you solve it. I think there's actually an easier way, so I'm maybe not a big fan of this question because often you want to use most efficient means. Here's another way to possibly solve it. So we can go to spreadsheets, and we'll set up X and Y for the movies, and we'll put our mid-interval values in: 75, 82.5, 87.5, 92.5, and 100. And then we'll put the frequency here. So there were 11 movies that had an average of 75, 51, 68, 47, and 23. In this case, we've got the runtime of these movies and then the frequency. So let's go ahead and try to find the average this way. Let's do stack calculations. And although we have 2 columns, we just have one variable. We just have runtime. That's the only variable. We don't have runtime as a function of a number, orders of popcorn or something like that. We're not comparing these two things of runtime and snacks that were ordered. We just have runtime, so just one variable. X, we placed in the X, and the frequency, we did have a frequency, the number of movies we placed in Y. And let's go ahead and find it out. And here it is. There's X bar, that's our average again, 88.15. Okay, so potentially a more efficient way, or yeah, potentially a quicker way as well. But if it's 3 marks, it looks like they want you to write out the mean formula. Okay, let's go back to the document and go on. Alright, so we have this table is used to create the following cumulative frequency graph. Use the cumulative frequency curve to estimate the interquartile range. Okay, so interquartile range, I believe this is actually given to you, it is given to you in your formula booklet. Interquartile range, IQR, is equal to Q3 minus Q1. So if we have, let's say, a box and whisker plot, for example, this is often where they're presented. Then we have, let's say, the median right here, and then the whiskers all the way to the max, and then the min. The IQR is the distance from Q1 to Q3. This is our interquartile range. So let's find Q1 and Q3, and then we'll subtract and find the distance between these two. So remember, our box plot divides everything up into quartiles. So 25%, essentially 25% in each of these quartiles, or it divides our data set up into 4 equal quarters. So if we have 200 movies here, we want to find the value where we have the where this marks where 25% of the movies will be less than this. And this Q3 will signify a point where we have 75% less than this individual point. So let's go ahead. 200 movies. Let's find for Q1, let's find the 25th, or that first quartile. And this is going to give us a value of 50. So we want to find the point where 50 movies are, or the point where the runtime of the movie that is greater than 25% of the other movies. In this case, 25% of 200 is that movie ranked 50 out of the 200. So let's see, this is 81, 82, 83, and this would be 84. So we know that Q1 is equal to 84. And let's find Q3. Q3 is going to be given by the 75th percentile, the movie or the runtime that is greater than 75% of the other movies. And this is going to give us a value of 150. Here we go. Important to bring a ruler, especially when the margins are pretty small. So this is actually 91, this is going to be 91.5 it looks like. This is 91.5. So Q3 is equal to 91.5. Okay. Let's see, use a cumulative frequency curve to estimate the interquartile range. So interquartile range, Q3 minus Q1, and this is going to give us a value of 7.5. Okay. And kind of guess what's coming next. Starfeud is a movie in the dataset and its running time is 100 minutes. Use your answer to part B to estimate whether Starfeud's running time is an outlier for this data. Okay, so if we have, let's draw one other box and whisker really quick. I can do a little better than that. So if we have another box and whisker, for example, and this is our interquartile range, let's set a median right here, and we have these whiskers. And the whiskers often extend to the max or the min. This would be, let's say, the min. This would be the max. But there are points in which there are data values that may lie beyond the main cluster of data points. And so the main cluster, or the central part of our let's say our data point, are clustered in this middle 50%, or what we call the IQR. And the question we're asking here is there a data point that lies far away from our main cluster of data? And how do we determine how far is too far? Well, if we're asking the question of, do these whiskers extend to reach this major, or sorry, one of these points on the outside? So, and these whiskers will extend 1.5 times the IQR. And if it's beyond that, if it's beyond 1.5 times IQR above Q3, or if it's 1.5 times IQR below Q1, then it's considered an outlier and it doesn't reach to this extreme point. So we know our IQR in this example right here was 7.5. And the question that we're asking is, okay, if we know Q3 itself is 91.5, this is equal to 91.5. These whiskers, which are going to extend 1.5 times IQR, are they long enough to grab this outlier, or is the outlier too far? Is it outside of the bounds of the main cluster of data? So let's write that out. Q3 plus 1.5 times IQR. Q3 is Q3 is 91.5, and 1.5 times IQR is 7.5. So I'm going to work that out on the calculator that I have right here. 1.5 times 7.5 plus 91.5 gives us a value of 102.75, or to 3 sig figs. I guess we could say 103, but actually let's keep the values as they are. 102.75. So is this star feud, which is 100 minutes, is it an outlier? Justify your answer. In this case, we could write 100 is less than 102.75. And since it's less than our maximum extreme point, we would say no, it's not an outlier. It's not an outlier. And this right here would be a justification, because this is our potential maximum point and it's within that range. It's less than this 102.75. Okay, so a little more here. Let's see what we have. Still in the realm of statistics and probability. It's believed that the running times of family movies follow a normal distribution with mean 88 minutes and standard deviation 6.75 minutes. So key hint already, we're in the realm of normal distributions, and they give us a mean of 88 minutes, standard deviation 6.75 minutes. It's decided to perform a chi-squared goodness of fit test on the data to determine whether the sample of 200 movies could have plausibly been drawn from an underlying distribution. That is to say, is this set or this sample of movies that we've gathered together, can it be modeled by a normal distribution where we have a mean of 88 and a standard deviation of 6.75? And that's the question. So part D asks us to write down the null and the alternative hypothesis. So let's go part D. We have a chi-squared goodness of fit. So we have two chi-squared tests. One's goodness of fit, one's independence. Independence test is blank is independent of blank. That's always our null hypothesis. And the alternative is blank is not independent of blank. But it's dangerous to confuse independent chi-square independence with chi-squared goodness of fit. Chi-squared goodness of fit is asking whether our distributions match. And in this case, we have a normal distribution. And we want to see, is the runtime of these movies approximately normal? That is to say, if we have some mean at 88, do we have a situation where we have a major cluster within one standard deviation, and so on and so on? And that's the question. Does this fit a normal distribution? And the null hypothesis would then be runtime of family movies. Runtime can be approximated or modeled by a normal distribution, or the alternative is that runtime is not approximated or modeled by a normal distribution. Alright, so that would be our null and alternative hypothesis. Potentially they might ask, and I think they actually do in this mark scheme, by a normal distribution with, and then we might want to say, sorry, this is a little messy, with mean of 88 and standard deviation of 6.75. In this case, potentially more detail. Just putting that at the end. Alright. As part of the test, the following table is created. Okay, so runtime less than 80 minutes. What we observe is there are 11. What we would expect is 63.6. So we would expect a certain percentage of our 200 movies to be less than 80. And we can find these values using our normal distribution. So let's go find this value of A right here. And it's between this interval of 85 and 90. What that means is, if we have this normal distribution centered at a mean of 88, the runtime of, let's say, movies that are 85 all the way to, let's say, 85 to 90, something like this, we can find the percentage of movies that we would expect to have within this range of 85 to 90, so it's not 90%, just minutes rather. And we can find the percentage of movies that we would expect, and if we know we have 200 movies altogether, we can find out how many movies we would expect to have within this range. So let's go back to the calculator to try to work this out. So, menu, probability, we're in the realm of distributions, and we want to use normal CDF. So the lower bound is going to be 85, our upper bound is going to be 90, our mean in this case is 88, and our standard deviation is 6.75. And so we're asking, what is the percentage, what are the percentage of movies that fall within this range of 85 and 90? And since it's continuous data, minutes, we don't need to put 84 or 91 for this. We just put the bounds themselves. Alright, and we have 0.288 or 28.8%. So let's go back to the document and work with that. So we have 28.8% is how much we would expect. 28.8% of our values we would expect to fall within this range. And that's not actually the value that we put in, because we have 200 movies and we would expect 28.8 or 0.288. Might as well put some of the other digits as well, just to make sure we get accuracy. But 3 is potentially okay. Generally you want to save as much accuracy as possible until you get to the end of the question. So roughly 28.8% of our 200. I'm going to work that out on the calculator that I have here. And so we would expect, for A, we would expect 57.6 movies for A. So A is equal to 57.6. And for B, B is going to be 95 and above. So we'll get a different color. What they're asking here is, okay, if a movie has a runtime of 95, what is the percentage of movies that are going to fall within this 95-minute runtime and above? So let's go back to the calculator and work this out. Okay. Menu, probability, distributions, normal CDF. Lower bound is 95. Upper bound for this, we can put 1,000, or if you want, you can put a very high number. 1,000 should be okay, 500 should be okay. Just want to make sure that you grab all of the movies that are to the right. Mean of 88, standard deviation of 6.75, and there we go. So 0.149859, roughly 14.9%. Let's go back to the document. Okay, so I'm going to use the same color of red. 0.149859. going to multiply this by 200, so roughly 15% of 200. I'm going to keep all of the decimals, just because we're not at the end of the answer. It's only at the end that we round to 3 sig figs. 9859 times 200. And we have 29.97, which we can round to 30. So B is equal to 30 movies. Okay, that looks good. All right, let's see what we can do from here. EI, or part 1 of E, sorry. Find the value of A and B. We did that. Hence perform the test to a 5% significance level, clearly stating the conclusion in context. So we want to run a chi-square goodness of fit. We've got our values, an observed and expected. Let's go ahead and run the test. So going back to the calculator for a sec. Let's get a new document, just because we used variables before. Go into spreadsheet. For this, I'm going to write observed and expected. You can always use X and Y, and it should be okay. So let's put in our observed values and the expected values. 23.6, 42.1, 57.6, 46.7, and 30. Okay. Got our observed and our expected. Let's run a statistical test. And we will do chi-squared goodness of fit. Observed, we called O, and expected degrees of freedom. What are degrees of freedom? Let's go back to the document for a sec. So as part of process, especially for an 8-mark question, we would almost certainly want to show degrees of freedom. Degrees of freedom for a chi-squared test, goodness of fit or independence, is equal to rows minus 1, columns minus 1. For a goodness of fit, we're always just going to have 2 columns here. So essentially it's always rows minus 1, but just for simplicity's sake and ease of memory, I suppose, we can always just use this. So rows, we have 1, 2, 3, 4, 5. 5 minus 1, and then 2 minus 1 if we want, we can write this. Degrees of freedom is 4. Okay, so let's go back to the calculator screen. Degrees of freedom is 4. Let's press OK. And we have a chi-squared value and a p-value. P-value of 0.016469. Okay. So let's go ahead and go back to the document. So what do we know? We have a p-value which is equal to 0.0165, I guess. And we had a significance level, I believe it was 10%, 5% significance level. So clearly stating the conclusion in context. So what we can write is we can write 0.0165, or what this is also equivalent to is 1.65%, multiplying this by 100 to just make it a percentage. And we can say that this is less than 0.05, this 5% above, or we can write this out. Either way should be okay. And our p-value is equal to 1.65. It's less than the significance level. Remember, a kind of intuitive way to remember this is just the probability that the null hypothesis is true. And 1.65% is very, very slim chance. We needed 5% or more to say that, hey, maybe the null hypothesis is true. In this case, 1.65%, very, very small chance that the null hypothesis is true, very small chance that we see these kind of results just based on probability alone. So in this case, we would reject, or sorry, better to write is fail, oh no, sorry, in this case we just reject. reject the null hypothesis, or H0. Reject the null hypothesis, and in context, we could say that runtime does not follow a normal distribution. Runtime does not follow a normal distribution with a mean of 88 minutes and a standard deviation of 6.75. Alright everybody, I hope that was helpful, and as always, best of luck. Take care.